All right, so let's talk acids and bases. We've introduced the idea before, but now we're going to be really formal about it, and we're going to use the tools of equilibrium, which we've studied now, to really get deeply into what acids and bases are and what they do and how to compare them and how to do calculations, how to measure them, etc. So all of this kind of revolves around this main reaction. The main reaction we call the autoionization of water. What is auto? What does that prefix stand for? Self. All right. So self-ionization. Water can react with itself to make ions. So this is the reaction, H2O plus H2O. Or if you prefer, you could just write 2H2O. They do this exchange where one of them takes H plus away from the other one. And so they make H3O plus and OH minus. This equilibrium is constantly going on in every sample of water ever. Okay? And we call the equilibrium constant for this Kw. Okay? So, first of all, how would I write the equilibrium expression for Kw, given the chemical equation I have up here? All right. So the initial instinct was to do concentration of H3O plus times concentration of OH minus over concentration of H2O squared. But I'm not going to do that. Well, why not? Water is a pure liquid. So pure liquids, they just go in as a value of 1 in our equilibrium expression. So I'm going to get rid of the H2O on the bottom. And so it's just concentration of H0 plus times concentration of OH minus is Kw. And this has a nice convenient value for us at room temperature. So this equals 1 times 10 to the negative 14th at 25 degrees Celsius. How would you characterize that value? Bless you. Solly? That is definitely a small k. All right. So that means, in pure water, there's very little H0 plus and OH minus. Turns out we can still actually measure it, even though it's very small. We have ways that we can measure what those concentrations are, but they are very, very small. All right, because this is a small k value. Now, what's going on here in reality, if we think about this reaction, and I'm going to draw something here. You're not responsible for being able to draw this kind of thing. But what's really going on here is one water molecule approaches another water molecule. And what kind of interaction does one water molecule have with another? Hydrogen bonding. Well, what's really going on here is hydrogen bonding taken to the extreme. So hydrogen bonding, remember, is an interaction between the partially negative oxygen of one water molecule and the partially positive hydrogen of another. What happens in this autoionization reaction is that hydrogen bond actually becomes a real bond, and the other bond breaks. So it's this lone pair on one oxygen kind of reaching out and grabbing the hydrogen from the other one and breaking that other bond. That's how we end up with H3O plus. Remember, H3O plus would look like this. And then OH minus looks like this. So that's what autoionization is. It's a hydrogen ion, what we call a proton, getting exchanged going back to when we introduced acids and bases the first time, why do we call H plus proton? Why are those two synonymous? All right, a hydrogen atom is usually one proton, one electron. You take away the electron, all that's left is the proton. So I will use the terms H plus and proton synonymously. Okay. H3O plus here, this ion has its own name. H3O plus is called the hydronium ion. So when you see references to hydronium, that's what they mean, the H3O plus ion. So this is an exchange of a proton from one water molecule to another. It makes two ions. Now, a lot of times we're lazy. And in fact, I will be guilty of this most of the time. Writing this thing out with two water molecules and then H3O plus and OH minus just feels cumbersome. So we will use as a shorthand for H3O plus, we will rewrite this reaction just this way. H2O breaks into H plus and OH minus. So then we would write Kw as concentration of H plus times concentration of OH minus. It's just shorter to write. Now the thing is, when we say H plus aqueous, I just want you to know that is shorthand for H3O plus. There's no such thing as just H plus on its own. H plus is a proton. It's got a positive charge. Unless you're out in the middle of space somewhere and there's no other atoms around, someone is going to share a pair of electrons with that H plus. So H plus on its own doesn't really exist. So just recognize this is shorthand for this. Free H plus doesn't really exist. Except in extreme situations, like I said. Out in the middle of space where there's no other atoms around to share electrons with it, sure, you could have H plus ions. I mean, in the sun, where you have a plasma where electrons have been ripped away from all the atoms, sure, you have H plus, but doesn't really exist in most chem lab settings. So whenever I say H plus, it's only because I'm lazy. It's only because I want to save myself from having to write the 3 and the O. That's it. Because we're going to write a lot of chemical equations involving H through O plus. And when you write them over and over and over, you end up saving quite a bit of time just by shortening it to H plus. All right, so we're going to be focusing on this equilibrium. H2O splitting into H plus and OH minus. So like I said, when I write this, remember that is a shorthand. So I've already said this, but I'll say it again. Kw, because this is important, I'm going to repeat it a lot. Kw equals concentration of H plus times concentration of OH minus. Which is equal to 10 to the negative 14th at 25 degrees Celsius. Couple of things I want you to note. When you change the temperature, you will change the K value. So at different temperatures, this value will be different. But for most problems, you should assume that it's at 25 degrees Celsius. All right. So if it's not specified, then assume that it's at 25 degrees Celsius. All right, the other thing I want to say is since concentration of H plus times concentration of OH minus equals a constant, when the concentration of H plus goes up, what does concentration of OH minus have to do? Go down. When the concentration of OH minus goes up, concentration of H plus has to go down. So this is important because in any water system, in any aqueous solution, if you add a source of H plus, concentration of H plus goes up, concentration of OH minus goes down. So this equilibrium is going to hold true in every aqueous solution that you encounter. The other good piece of news about this is if I know how to measure one of these concentrations, I can always find out the other one. So if I know the concentration of H plus, I can automatically calculate concentration of OH minus. If I know the concentration of OH minus, I can automatically calculate concentration of H plus. All right. So if you know one, you can calculate the other. All right. So the rest of this unit is going to be, well, what are the things that we can add to a solution that will make these concentrations change? All right. It turns out that for reactions, for biological systems, for everything, really these two concentrations are super important. You change the concentrations by a little bit, you might kill something. You change the concentrations by a little bit, the flowers in your garden might produce purple flowers instead of blue flowers or instead of pink flowers. You know, there are lots of things that these concentrations govern. So we can add acids. An acid is anything that will increase the concentration of H plus. Bases are compounds that will increase the concentration of OH minus. And we already said when one goes up, the other one has to go down. So we have a couple of definitions. When you think of acids, I want you to think of this really simplified definition. acids are H plus, bases OH minus. So that should be the first thing you think of. Acid, H plus, base, OH minus. But then we have some more specific definitions because there are actually different mechanisms by which you can change these concentrations. So there's an old historical definition of acids called the Arrhenius definition, and I'm not even going to bother giving you that one because it's just a vocabulary word. It's just some old, hard-to-spell name. But the two definitions that come up most would be the Bronsted-Lowry definition and the Lewis definition. All right. If I just say acid, then we're really referring to the Bronsted-Lowry definition. So if I just say acid or I just say base, then this first definition is the one that I go with. So this is the common definition of acid. And a Bronsted-Lowry acid is an H plus donor. So in other words, it's a compound that water can walk up to and say, hey, I'd like H plus. And the acid gives over H plus. All right. So there's just a direct correlation. A Bronsted-Lowry acid automatically increases the concentration of H plus because it's actually just giving H plus away to water. The Lewis definition, now this is one that if you want to refer to this definition, you always put the Lewis in front. So if I just say acid, I'm referring to the Bronsted-Lowry definition. If I say Lewis acid, I'm referring to this definition. A Lewis acid is an electron pair acceptor. So it's a molecule or an ion that another molecule or ion can come along with a lone pair and share it with that Lewis acid. All right, the two definitions might seem kind of at odds with each other, but what I want to do is show you how they're completely compatible and how Lewis acids can turn out to produce more H plus in a solution, even though the definition doesn't say anything about H plus. The definition of a Lewis acid has nothing to do with H plus. All right. So to give you an example of Bronsted-Lowry acids, on the next slide we have what? HCl. We've seen HCl before. How does HCl act as a Bronsted-Lowry acid? What happens when you put it in water? All right, so I want to just correct one vocabulary word. So the response was it dissolves into H plus and Cl minus, or H3O plus and Cl minus. But what was the word? It's different from dissolve. Dissociate. So I want to make sure we're clear. Things can dissolve and be dissolved in water, but not dissociate. So when we want to talk about splitting up, we want to talk about dissociation. So for example, hydrochloric acid, you put it in water, and, well, HCl looks like this. I'm just drawing it backwards. And H2O looks like this. And what's happening is water's going to come along and take the hydrogen away. Again, you're not responsible for drawing these little curved arrows showing how the electrons are getting shared. That's something you'll do more when you take organic chemistry someday. But I like the visual because it's the idea, all right, we're thinking about this reaction. These are all elementary steps where it's just one collision where this water molecule bumps into an HCl molecule and forms a bond to the hydrogen and breaks the HCl bond. So they would make H3O plus and Cl minus. Right, after this is done, we get Cl minus. Oh, I'm going to switch sides. Cl minus looks like this. It now has 4 lone pairs and then H3O plus. Now, this is probably, again, the last time you'll see me write this equation this way. Because if I wanted to write this equation, I would leave the water out, and I would just write HCl turns into what plus what? H plus plus OH minus. H plus plus Cl minus. So Bronsted-Lowry acid is just something that parts with its proton with relatively little resistance. I was trying to come up with an alliteration there. Parts with its proton with paltry protestation. How about that? So an acid parts with its proton. It turns out Lewis acids, even though they don't actually have H plus, can make a solution turn acidic. They can increase the H plus concentration. So what do I mean by Lewis acids? Let me give you an example. Most Lewis acids are positive ions, although not all. Some examples. So one would be boron compounds often make good Lewis acids. BF3, boron trifluoride. This is an outstanding Lewis acid. Any idea why? Well, let's take a look back at our definition. Our definition of Lewis acid was an electron pair acceptor. Why would BF3 make a great electron pair acceptor? Benny? All right, fluoride's highly electronegative, so the fluorines are like, hungry for electrons. But there's another thing here that makes this a great electron pair acceptor. Well, there's a lot of lone pairs, but we're talking about accepting more electrons. So the lone pairs aren't really what's helping it be an electron pair acceptor. Boron's missing electrons. Boron's not following the octet rule right now. So boron has space. It has basically orbitals available. It has an empty orbital available ready to make a new bond. So if something with a lone pair comes along, like say water, actually I'm gonna leave it generic. I'm just gonna write X. If something with a lone pair comes along, it can easily share that lone pair with the boron because boron has extra space. So note, this is a Lewis acid because it's accepting a pair of electrons to make a new covalent bond. Lewis acids aren't things that actually steal pairs of electrons. Nothing ever actually steals pairs of electrons. But it's something comes along with a pair of electrons, and then they decide to share it. Okay. More commonly, what we see as Lewis acids would be metal ions, particularly transition metal ions. So, for example, we could take iron 3+. Why would a metal ion make a good electron pair acceptor? Why would something with a lone pair see a metal ion and say, hey, why don't I share with you? Because it's really positive, right? If you're a lone pair, you look out at the world and you're like, hey, I'm a lone pair. I love positive things because you're negatively charged, right? You know, so often the answer in this class is Coulomb's law, opposites attract. So what metal ions do is they gather up things with lone pairs. So things with lone pairs tend to bond with them. We just saw this in the Le Chatelier's principle lab. So actually I'm going to change this. Instead of iron 3+, I'm going to use the example from that lab, which was cobalt 2+. So we saw that cobalt 2+, when you dissolve it in water, actually gets surrounded by 6 water molecules. It's got such a positive charge that water molecules come along and they all decide, hey, I'd like to share with you. Turns out 6 of them did it. So these 6 water molecules will all converge and decide, hey, you've got a positive charge. I like your attitude. Let's bond. So we said it actually forms this complex where you've got the 6 water molecules surrounding it. So cobalt there is acting as a Lewis acid. What questions do you have about that? This definition of a Lewis acid. All right, so how is this related to, we said acids make H+, right? That was our acids or compounds that increase the concentration of H+. So how is this Lewis definition even related to that? Well, it turns out when you put a Lewis acid in water, who's got lone pairs in water? In a water solution, who's got lone pairs? Oxygen, the oxygen from the water molecules. So if you put a Lewis acid in water, it's going to end up surrounded by water molecules. Water molecules are going to bond with it. So if you add a Lewis acid to water, water will bond with it. The classic example, the one we're going to see the most in our calculations involving H plus will be aluminum 3 plus ion. I can explain the reasons for that later. But if I dissolve aluminum 3 plus in water, really it's going to get surrounded by water molecules. So it'll make a complex just like cobalt did. Now, if you're hydrogen and you've been bonded to oxygen for a long time, you've had a nice stable relationship, you've been totally happy, how do you feel when oxygen decides, you know what, I'm not happy enough just to have my 2 hydrogens. I need another bond because this aluminum 3 plus, I mean, it's super attractive. How does hydrogen feel about that? Yeah, not so great. Now I'm ascribing feelings that don't really exist. But the point is, when the oxygen makes the bond to the aluminum, that weakens the oxygen-hydrogen bonds just a little tiny bit. Okay? Remember, the hydrogens are partially positive, and now you've got this aluminum with a +3 charge that repels the hydrogens a little bit. So what can happen is one of these hydrogens now becomes easier to remove. And so the OH bonds are slightly weaker, and the hydrogen is slightly easier to remove now. And so what can happen is H plus can split off of this, or another water molecule comes along and grabs H plus off of it. Makes H3O plus. So if I remove this hydrogen here, I leave behind now an ion with a 2 plus charge, but I've now created an H plus. So that Lewis definition that doesn't seem to have anything to do with H plus, turns out if you put a Lewis acid in water, because the Lewis acid bonds to water and then weakens the OH bond in water, it actually does produce more H plus. Yep. All right, so the question is, does this happen to every aluminum ion? And the answer is, what we're going to see is some acids are more willing to split up than others. And was this Al H2O6 3 plus ion, was that one of our strong acids? No, it's not one of our strong acids. And we know and I'll remind you in a minute, we know that strong acids are the ones that every molecule splits up. So this would fall in the weak acid category. It turns out, when you dissolve aluminum 3 plus in water, maybe 1 out of every 100 of these complexes, H plus will break off of at any point in time, and it'll establish an equilibrium. So, yeah, really, I should say this is an equilibrium. It's reversible, and it's going to have a K value that we can look up. Generally, this first step, though, does happen to completely. Every aluminum 3 plus ion you dissolve will get surrounded by 6 water molecules. So that first step happens completely, but then this dissociation is only going to be a small percentage of the molecules will do that. Other questions? All right, that's what I mean when I talk about acids. When I talk about bases, what do I mean? Well, Bronsted-Lowry definition of a base is going to be any molecule that takes H+. It's going to be an H+ acceptor. Now, I said earlier that you should think of bases as things that produce OH-. Why would something that accepts H+, why would that produce OH-? Okay. All right, so one way to look at it is if you're something that's taking H+ away. We go back to our equilibrium here. If I take H+ away, we said if the concentration of H+ goes down, concentration of OH- is going to have to go up. So from that equilibrium perspective, like looking at that equilibrium expression, we can say anything that takes H pluses away is going to produce more H-. There's a simpler way to think of it too. If I put an H+ acceptor into water, who's it going to take H+ from? Water. And what does that produce? OH-. All right, so this is going to be any molecule or ion that can take H+ away from water to produce OH-. So OH- is by definition a Bronsted-Lowry base because OH- can take H+ away from water. And it just makes another OH- in return. I'll come back to the Lewis definition in a minute. So for example, ammonia is our classic example of a Bronsted base. When you react NH3 with H2O, I have NH3 like this with a lone pair. I have H2O like that. The nitrogen reaches out and grabs hydrogen and breaks the OH bond. What is that going to make? All right, it's going to make NH4 and OH. But there's something missing. NH4 plus, and OH minus. Because the nitrogen now has 4 bonds, right? So the nitrogen is going to have a positive formal charge, and the OH minus, the oxygen has 1 bond and 3 lone pairs. It's now got a negative formal charge. So I want you to do the same thing. Write a base dissociation reaction for CH3NH2, also known for Breaking Bad fans out there. CH3 is a methyl group. NH2 is an amine group, so it's methylamine. That's the precursor that they steal. That's the key molecule in their synthesis. Yeah. So I want to summarize a conversation that just took place in the classroom. I didn't want to include all the babbling in the recording, but the bottom line was I was saying that making meth is poisoning people for a living, and I personally, whether or not I could figure out how to do it, I would consider such a move so opposed to my personal worldview, and so opposed to everything that I value that I've never even entertained the possibility at all. All right, so we have methylamine down here. How did you write your dissociation reaction? What are the reactants? All right, CH3NH2 plus what? H2O. What would it make? CH3, NH3 plus, and OH minus. All right. So anytime you have a Bronsted base and you want to write its equilibrium, that occurs when you put it in water, that's how you do it. Base plus water makes this thing over here that we're going to call the conjugate acid plus OH minus. Yep. Oh, so the question is, would it have mattered if I had written CH4NH2 plus? Is that okay? So my response is, I mean, technically, yeah, it's still the same formula. Why did I write CH3NH3 plus? Yeah, the new H plus is going to bond to the lone pair on the end. So this is CH3NH2 here with a lone pair on the nitrogen. If you think about where that's going to add a proton, it's going to add it to the nitrogen. So that's why I wrote the formula the way I did. And that's why I would say CH4NH2 plus, where not technically wrong, but it's wrong enough that I wouldn't write it. I mean, technically you could write CH6N plus if you wanted to. But again, CH3NH3 plus just contains more information. All right, so just to very quickly finish, a Lewis base is anything that has a lone pair that it can share to make a bond. All right. So this is an electron pair donor. Meaning any molecule or ion that can share its lone pair with a Lewis acid to make a bond. And I'll leave it there. Next time we'll move on to, all right, how are acids and bases related to each other? How do we know how strong they are, etc.? Yeah, student question is this the same Lewis from Lewis dot structures? And it is. Gilbert N. Lewis is a giant in the history of chemistry.